Welcome back. Last time we talked about exponential growth and decay, and we got a feel for what the function looked like. Remember, the parent function of exponential growth or decay looks like y equals a times b to the x power, where a is the initial amount and b is either the growth or decay rate. And then x is our exponent. These are our transcendental functions. X has transcended up into, exponent land. And that usually represents time. So how much time has passed or how many growth or decay periods. So today we're going to take a look at shifting the exponential parent function and then evaluating with a natural base of e. So if we take our parent function and we have an a that is greater than 1, so if a is greater than 1, what's going to happen is we will have a stretched out parent function. So, yesterday we talked about this is like y equals something to the x power. If you multiply it by an a, it's going to make it more stretchy. So this would be y times y equals a times b to the x, where a is greater than 1. Now, if we want to compress it down, we would have an a value between 0 and 1. So a compressed graph might be like this. So it's like we're stepping on it and smashing it down. A times b to the x, where a is between 0 and 1. If we take and multiply a times -1, then we get a reflection. And this is going to be a reflection over the x-axis. And then if we want to shift our graph horizontally, remember that's counterintuitive or the opposite of what you would think. What's going to happen there is we're going to have something that looks like y equals a times b to the x plus c to move us to the left, or x minus c, which would move us to the right. So with horizontal translations and the quadratic parent family, or the quadratic family, or the absolute value family, or the square root family, remember that the plus or minus, the constant happens within the argument. So inside those absolute value bars, or inside something being raised to the second power, or underneath the radical. Now, a vertical translation will happen when we take and add or subtract something outside of the argument. So this will shift us up. If we did minus c, that would shift us down. All right, then let's take a look at this example. We're going to graph the parent function and the translation left 2 and down 3. I'm going to introduce you to something today, and that is y equals e to the x. And e is the natural base. Natural base. So e is a number, it's kind of like pi. It's a transcendental number. It has a real meaning. I'm not going to go into what the meaning is. It's the limit of 1 over n plus 1 or something like that. E comes from the last name of a Swiss mathematician, Leonhard Euler. It sounds like Euler, but it's spelled E-U-L-E-R. And anyway, he was a mathematician that came up with this natural base, and he just found that in nature, most exponential growth kind of follows this pattern where your base is about 2.72-ish. Okay, so we're going to graph the parent function and then the translation left 2 and down 3. So with the parent function, so here's the parent, y equals e to the x. I can think of some table or a table of values here if I wanted, but I'm just going to do this out loud. If I plug in 0, I'm going to get out 1 because e to the 0 is 1. If I plug in 1, I'm going to get about 2.72, so that's going to be right about there. And if I plug in -1, that would be 1 over 2.72, and that's going to be something pretty close to 0. Okay, so this is the parent function, y equals e to the x. Now it approaches an asymptote at as it moves towards the far left. As it moves towards negative infinity, this line or curve rather is going to get closer and closer and closer to 0, making the horizontal axis an asymptote. Okay, then let's look at these translations. So as far as the translations go, can you write a new function? Sure you can. Y equals e to the, well, we need to go left 2, so that's going to look like x minus 2, and then down 3. So y equals e to the x minus 2. Nope, I'm going to change that. Left, look back at your rules. Left would be x plus c, and then down would be minus 3. Okay, so I'm just going to take this curve now. I'm going to do it in a different color. How about maybe something a little lighter blue? Left 2 and down 3. So I'm going to start at this point, and I'm going to go left 2, 1, 2, down 3. That puts me right here. Now I'm going to take this point, and I'm going to go down. Well, actually, I want to go left first. So here's left 2, and then down 1, 2, 3, right about here. And then, oh, I don't know, how about if we take this point here? We're going to go to the left 2, and then down 1, 2, 3, right about here. Here's my new curve. And this is y equals e to the x plus 2 minus 3. Okay, I'm going to just kind of erase some of this junk. This looks messy. Okay, well, whatever. All right, we kind of cleaned that up. So that's how we would translate an exponential function. I think that's all I have to say about that. Oh, it also asks for the domain and the range. So before we move on, let's talk about the domain. So with our parent function, the domain is going to be from negative infinity to positive infinity. I can raise e to anything. But if we look at the graph, I'm never going to be able to get out a 0. So my range is from 0 to infinity. And notice I used a soft parenthesis at 0, or an open interval there at 0. There's nothing I can plug in for x to turn y to a 0, or to create a 0. All right, and then for our translated function, just look at your picture here. Again, my domain will be from negative infinity to positive infinity, but the range, it looks like my new asymptote has shifted down 3, so my range will be from negative 3 to infinity. Again, I'm using a open bracket. Here's that asymptote for the original function. Here's that asymptote for the function that's been shifted down 3. Okay, now turn the page and let's take a look at this table of values. It says the best temperature to brew coffee is between 195 degrees and 205 degrees. Coffee is cool enough to drink at 185 degrees. The table shows readings from a sample cup of coffee. How long does it take for the cup of coffee to cool enough to drink? We're going to make an exponential model. All right, so here's where I'm going to open up my calculator. And how much do you remember about a regression? So stat, edit, and then I need to enter the information. So I'm going to go and clear L1, I'm going to clear L2, and then I'm going to enter my times in L1 and my temperatures in L2. So this is kind of boring to watch, but it's good practice. And then in L2, here are my temperatures: 203, 177, 153, 137, 121, 111, and 104. Okay, then I'm going to set my viewing window. My times were from like 0 to 30, so I'm going to say, how about from 0 to 50 in increments of 5 minutes. And then my minimum temperature is probably going to be, I want it to be maybe 100. And then my maximum temperature, maybe 215. And let's scale that by units of 10. Okay, let's look at a picture. Oh, you know why I don't see my picture? My scatter plot's not on. So second y equals, I need to turn my stat plot on. So toggle that on and hit graph. Beautiful. There's my scatter plot of those data points. And then I go back to stat, over to calc. Now this time I want to do an exponential regression, and an exponential regression is 0. So arrow down to 0, hit enter, enter through this information, and there we go. Y equals 196.657 times 0.978 to the x power. So notice that b is less than 1. And that makes sense. That means that this is decay, right? My temperature is going down. Okay, so I'm going to record that here in my notes. Please do that with me. So my exponential model is y equals 196.657 times 0.978 to the x power. Okay, back to my picture here. Now what I'm going to do is I'm going to transfer that into my y equals so that I can watch this curve be drawn and then I can use it. Okay, so I entered the graph, or I entered the equation, and I hit the graph, and beautiful, that fits really nicely. It cuts through most all of those points. Then, second trace, I'm going to calculate a value at, well, I want to type in 185, but that's going to give me an error message. That doesn't make any sense. Okay, so I want to know how long does it take for the cup of coffee to be cool enough to drink? So instead of calculating, I'm just going to trace. Watch me trace my curve. Actually, I don't think I'm on the curve. Now I'm on the curve. And I'm watching my temperature, which is Y. I'm watching Y. I'm looking for 185 degrees. I'm getting close. 180, there we go, 185 is right about there, close enough. So it says at 2.6 minutes, the temperature will be whoops, where'd my graph go? It'll be approximately 185 degrees. So again, I just traced the curve. So I'm going to say at approximately 2.5 minutes. All right, so that takes care of that. An exponential model, we can make an exponential model. I mean, we can really make any shape model. So that's a cool one. All right, let's go on to example 3. And this is going to go pretty quick and easy, so hang with me just a few more minutes, or a few more seconds, really. I want to evaluate each expression to 4 decimal places. So e to the 5th power, I'm thinking, well, that's going to be like 2.72-ish to the 5th power. I don't know what that's going to be, but on my calculator, my E button is second ln. Whoops, let's get out of this. Second ln. That didn't work either. Clear. Second ln. Come on. And then if I just plug in a 5, I'll get 148.4. So that is exactly 148.4. If I want to be a little bit more exact, I would round to 3 decimal places. So 13413. Okay, I want you guys to take a minute and come up with B and C, and then we will pick up with example 4 tomorrow. So you guys come up with answers for B and C, and then we'll do number 4 tomorrow. See you tomorrow.